So those were the prizes, so thank you very much, Mr. Decker. That was a big moment in this evening. You know how it continues. 2 new particles, they will be shown to you tonight, held in front of you. Long predicted, last year discovered. There will be 2 presentations, one by Leo Kouwenhoven. Mr. Majorana, he really doesn't need any introduction. And the second by Stan Benvelsen, whom we had to convince to come here because he gets so many invitations, but he was willing to do that too. So the 2 representatives of 2 communities will present 2 new particles to you tonight, and we start with Leo. Leo, could I invite you to come forth?
Thank you very much. Yes, Majorana and Higgs. 2 names. I have 2 physicists, Ettore Majorana and Peter Higgs. And 2 names for 2 particles, the Majorana fermion and the Higgs boson. And both these 2 particles were predicted decades ago, like the Higgs particle in the 60s and the Majorana already in the 30s. And after decades of searches, both particles were discovered in the same year, 2012. Now, dear particle physics friends, we condensed matter physicists do not get to discover a particle very often. And did you really have to claim the Higgs in the same year as we had the Majorana? And I believe I am here at the battle, right? I am here at the Majorana-Higgs battle. So if this is, I hope this is the right occasion. So now our search for the Majorana was right away sponsored from the beginning by FOM. And I'd like to actually acknowledge FOM for their support over the years, and I hope you still have something in your glass. And thank FOM, and actually who is FOM? Well, FOM is actually everybody here. We all together form FOM. So I'd like to thank all of you and actually bring out a toast. And the toast is that I hope that also 2013 will be a great year for physics. Cheers. Now let me set this up a little better. Now we all know, sorry. Oops. Okay. So we all know that the Higgs was discovered in CERN, in this large LHC accelerator. And the radius of the LHC is about 10 kilometers. And this thing had to be so big in order to reach the very high energies necessary to probe the Higgs. Okay? The energy scale for the collisions is of order tera electron volts. Now, for the signatures, to measure the Majorana fermion signatures, we actually had a different setup. We were using a small nanoscale device with a radius of about 10 nanometer. So compared to the LHC, that is 12 orders of magnitude smaller than the LHC. But even more important, or more relevant I would say, the energy scale that we were probing for the Majoranas was very small. So we actually had to cool down the sample to very low temperatures and probe it at micro electron volts. So that is 18 orders of magnitude different from the Higgs scale. And so whereas the Higgs setup went up to the highest energies, for the Majoranas we had to cool down the system and probe it at the very lowest energies. Now, to probe these, or to make these high energies for the Higgs, there was a large international collaboration with, I believe, thousands of contributing scientists that designed the LHC, constructed the LHC, and also used it for the experiments. Now, it's actually thousands is a large number. It's actually more than we have here today in Veldhoven. Now, our team for the Majoranas is actually quite a bit smaller. And so here you see actually all 6 authors on our paper, and starting with 2 graduate students, Koen Zhou and Vincent Maurik, a postdoc Sergei Frolov, and our collaborators from Eindhoven, Sebastian Plissard and Erik Bakkers. Now, there is actually an advantage of having such a small team, because I could take the entire team out for free beers at a cafe in Delft. And on this day, we were actually celebrating, it was in May this year, when our paper came out. Now let me try to make a slight change here. Yeah. So this was a nice celebration, but are we really certain that we actually did detect the right particle? Were the Higgs people actually absolutely certain? Well, the Higgs experiment claims a 5 sigma accuracy that they have a particle. And in terms of percentages, it's 5 or 6 nines. So they're very sure. And can we also give you a number for our Majorana detection? In a similar number, hopefully. Well, we know, and it's actually also with absolute certainty, that the accuracy to which we can claim that we have detected a Majorana fermion is pretty sure. So as you see, the Higgs and the Majorana are actually 2 entirely different experiments. The Higgs probes the fundamental particles in our universe, and our motivation for the Majorana fermion is actually computing. It's our wish to make a quantum computer, and the Majorana fermion could play an important role there. Now that's funny, right? That a particle could have some significance for a computer. So how can that be? Well, let's define what is a Majorana fermion. It's actually not so difficult. A Majorana fermion is a fermion that is equal to its own antiparticle. And in terms of quantum operators, what you say is that the operator to create a particle is the same as the annihilation operator. Or you can say that to create a particle is the same operation as to create the antiparticle. It's the same statement. Now, to explain this analogy, or to explain this symmetry, I should say, the best analogy that I have is actually a half-filled glass. Because we know that a half-filled glass is actually the same as a half-empty glass. And I can actually associate the particle with the filled part of the glass and the antiparticle with the empty part. Now this analogy actually, you may think that's a silly analogy, but it actually works very well. And with this analogy, if you can keep this analogy in mind, then you can carry on, or you can, and if suppose I would lose you, you can always fall back on this half-filled glass theory and follow up on the story. So please don't drink your glass completely empty, but keep it at least half-filled. So we have the definition. And this definition immediately implies 3 things. Because of the symmetry relation, the particle cannot have energy, cannot have charge, and cannot have spin. Because if it would have charge, the antiparticle would have the opposite spin, and also for the energy and the spin. So all these properties, energy, spin, and charge, should be equal to 0. And that's a lot of nothing for an important particle. In fact, I would say it's 3 keer niks. That's 3 times nothing. And just for the sake of tonight's event and the comparison with the Higgs particle, I'd like to rename our particle just for tonight. Just forget about it later on. But just for tonight, I would call it the Nix particle. 3 keer niks. Higgs and the Nix. Now, to have Nix, that's actually that's okay for us. But it does pose a problem. how do you actually measure NICs? What kind of detector can you use that actually can find a Majorana? It gives you a click when it finds a Majorana. What interaction can it have with the detector? And that is a very good question. And actually, that is also the reason why the Majorana fermion was so far not detected. It's so difficult. Now, there's actually a sad similarity between the particle and the man Ettore Majorana. Ettore Majorana predicted his particle in 1937, and it was a big success. He immediately got a professor job in Naples, but somehow this success and everything bothered him. Maybe these were psychological reasons, or maybe he didn't want to live in those years right before the Second World War in Italy. That was fascist Italy. And that someday, it was actually in March 1938, he was done with everything and everybody. And what he did was, he took a boat from Naples to Palermo. People saw him buying a ticket, and he went onto the boat. But that was the last thing that actually people saw of him. So since then, March 1938, also the man, Ettore Majorana, has never been detected anymore. So searches have been going on for both the man and the particle. And this is a search for the man. Ci l'ha visto, did you see him? Asking you, did you, we're still looking for him. But we have signatures. I'm going to show you some signatures of the particle, the Majorana fermion. And at the end of this presentation, I also want to show you a glimpse of the man, Ettore Majorana. We also have a signature of Ettore. Okay, so Majorana predicted his particle, and he was thinking about particles that could live free in the cosmos, maybe particles like a neutrino. And since then, there have been searches for the Majorana fermion in large-scale detector facilities. And this is a picture of an underground lab in South Dakota in the United States. And it's really big because here, actually in the tunnel, you see a train coming in. So that sets the scale of the lab. It's huge. It's probably as big as this whole thing here. But even at this handful of locations worldwide, so far there has been no positive signal of a Majorana fermion, a cosmic Majorana fermion. Nothing. The latest results are 0. So if it's so difficult to find a free Majorana in the cosmos, and at some point, after all these decades, it becomes worthwhile to maybe consider an alternative approach. So instead of looking for free Majoranas, could we maybe make or construct a Majorana fermion? Could we, by adding things together, make a particle that has all the properties satisfying Majorana's equation? And if it does so, I think we can call it a Majorana. So what can we do with that idea? Can we construct a Majorana? So how would it work? Well, the idea is actually very simple. Suppose you would like to construct a particle called a train. What you do is you take elementary particles, wagons, you connect them together, you put them on a rail, and there you have a train. Now, what is important to realize about a train is that the wagons are now completely frozen. The internal degrees of freedom of the train is 0. The wagons can no longer move, it's only the train that can move as a whole. And for simplicity, we can just forget about all these many wagons, and we just talk about the train, because that's the only thing that moves. So can we take this concept and make a Majorana fermion in a similar way? Now, to quote Barack Obama, very timely, we say, yes, we can. So what we do, again, we take a row, in this case, a row of electrons, and we put them in a very thin, one-dimensional wire. And all these orange circles are electrons. They fill up the wire completely, except for the seat on the very left end. Now these are particles, antiparticles. They're pairs. My circles, in this case, are electrons. And the empty circle is a hole, the absence. So it's not a positron, but it's the absence of an electron, and that's called a hole in condensed matter physics. Now we can move all these electrons. Now, can you please move over by one seat? That's a small change for each electron, but what it does is it fills up the seat on the left. But simultaneously, it opens up the seat on the right. So a small step for each electron, just one seat, move one seat over, is actually a big jump for the hole. It jumps completely over to the other side. Now, you can ask this again and again, and as you see, the hole is jumping back and forth. Now let's, again, the same as with the wagons in the train, let's also here forget about all these electrons and just focus on the jumping hole. And the jumping hole, it's now jumping back and forth, but we know from quantum mechanics if something can be at two locations at the same time, it can be in a superposition. And that's also here the case, that the hole is actually on the left side and the right side simultaneously. It's a spatial superposition of the hole being left and right at the same time. Now, I want to make another transformation, another change of focus. I don't want to think about the jumping hole back and forth. I just want to now focus on one of these end states. The left one or the right one. And the end state is also a superposition, but not a spatial superposition. In this case, it's a superposition of two particles. It's a superposition of an electron and a hole. And so we've made a transformation of a jumping hole back and forth to a superposition of two particles. This end particle, which is a superposition of the hole and the electron, and similar on the right side. So here we're back to our half-filled glass. It's half-filled, half-empty. And since we know that the half-filled glass is the same as the half-empty glass, then also my half-filled circles must be Majoranas. That's the proof. If you want to be a bit more accurate, then there's actually a definition that the Majorana is indeed the superposition of an electron and a hole. And it has to be, in order to be a Majorana, it has to be an exact equal superposition. So that sets the factor 1/2 in front. It has to be this 1/2. Now, in order to get this factor 1/2 in front, you actually have to connect your nanowire with a superconductor that imposes actually the factor 1/2. And you have to apply a magnetic field. So the superconductor in the presence of a magnetic field, and the magnetic field breaks time reversal symmetry, and that together, then you can show that these two end states indeed correspond to the Majorana equation of particle equals antiparticle. So this is our construction, and I think it's a brilliant construction of how to construct a Majorana fermion. Unfortunately, I must admit that I didn't think of this construction at first. It's actually work that has developed over the past decade, starting with theoretical concepts from Alexei Kitaev in 2001. And there was a very important improvement by Charlie Kane. And Charlie Kane was a plenary speaker here last year. I hope you remember Charlie Kane. And then the translation from these theories to proposed devices that we can actually test these theories were made by our own Carlo Beenakker and this group in Leiden. So including Anton Akhmerov, who just got the thesis prize. Now that work led to two specific recipes in 2010. There were two papers from Lucien Sau and Sarma, and also from Orek, Raphael, and Van Oppen, that translated the Beenakker concept in very specific recipes for how to construct a Majorana fermion. And the pictures that I show you here is just a cartoon translation of the Hamiltonians that you can find in these two papers. So we're all set. And so we know the recipe. It takes nanowires. And actually, we were already working in 2010 for some years on semiconductor nanowires. So we were ready to enter the field. So we quickly talked to our collaborators in Eindhoven, Sebastian Pizarre and Erik Bakkers, and decided to grow indium and timonite semiconductor nanowires. Very thin, about 100 nanometer diameter, and lengths of a few micrometers. What we do is when we get these wires in Delft, is we take the wire, just really one by one, break it off, and it breaks off at the stem at the bottom where it is thin. And we take it and put it gently on a substrate. And the wire that you see here is colorized in green, and it's on a blue substrate. And this blue substrate is actually a dielectric, an insulator. And underneath the insulator, I hope you can still see it, you see some metallic strips already buried inside the sample, inside the substrate. And these are our gate electrodes. If we apply voltages to these gates, we can set the electrostatic potential landscape in this region of the nanowire. And so we have a knob to change or to make and to break the Majorana fermions. So then we put the wire on top. We make an electrical contact up here, that's gold. That's a normal metal. An electrical contact down here in red, that's a superconductor. And this superconductor is made of niobium titanium nitride. And that's a superconductor developed in the group of Teun Klapwijk in Delft. And it's actually very good because it's a very strong superconductor, and it even persists in a high magnetic field. And that's exactly what we need. And so we have our system, and under the right circumstances, by applying a magnetic field, we hope that at these two locations we will find our Majorana fermions, at the end points where the superconductor overlaps with the nanowire. Now in the metal, we have normal electrons, so a normal circle, and in the superconductor we know that electrons actually pair up in pairs that we know as Cooper pairs. So how, if we send, oh, excuse me, that was the answer. So how can we direct this electron towards the Majorana, and in such a way that by interacting with the Majorana, it converts into a Cooper pair in the superconductor. We have a full circle, and we have a half-filled glass. So how can that lead to two full glasses? Now, at this point, you have to realize that the half-filled glass is actually a superposition of a full glass and an empty glass, shown up there. And so if the electron comes in and it takes the full part of the Majorana superposition, then it can pair up in a Cooper pair and enter the superconductor. And in that case, we can detect a little current from sending in the electron. It takes the full glass from the Majorana, pairs up as a Cooper pair, and continues. It gives you a little signal in the electrical signal in your measurement. So we try to actually also show you a little animation. So what we've done here is first show you what you should expect at zero magnetic field when there are no Majoranas. There's nothing there, there's an electron coming in from the gold, and it shoots at the superconductor, but there's nobody to pair up with and has to go back. Yeah? So that leads to an electrical measurement. And what you see in this graph is on the horizontal axis, that's the voltage. And when the voltage equals 0, we have energy equals 0. So this is 0 energy. Then we measure the conductance. It's a derivative of the current to the voltage. And you see that this conductance near small energies, 0 energy, is strongly suppressed, showing that the electron indeed cannot enter the superconductor. It's reflected. Okay? Now the next thing is to apply a magnetic field in such a way that we actually introduce Majoranas at these two endpoints, one at the beginning, also one at the very end. In this case, we're first going to send an electron at finite energy, so the wrong energy. It cannot interact with the Majorana because the Majorana is at 0 energy, and it has to go back. If we adjust now the energy, so now we have 0 energy, the incoming electron can interact with the Majorana, take the full glass of the Majorana, pair up, and becomes a Cooper pair in the superconductor, and contributes a little bit to the current. So that's the proposed measurements. By interacting normal electrons with the Majorana, we can detect something. So here we are, again, the same curve at zero magnetic field, where you see a suppression of the conductance near small energies. Near zero energy, there's no current flowing, right here. And you would expect that if you apply a magnetic field and you introduce the Majoranas, that near zero energy, there should actually be an enhancement of the current. And then you can go in and lead to a little bit of extra current. So if we take these curves, as you see here, but now start to increase the magnetic field, we get a sequence of traces. And at some point, we find that near zero energy, indeed, a peak starts to appear. And if you've drunk your glass completely, I may actually help you, guide your eyes, because these are the peaks, what it's all about. So within this circle, the peaks that you see near zero energy, these are the peaks that we were looking for. They are zero energy, but maybe even more important is that if we change magnetic field, here from about 100 millitesla to 400 millitesla, the peak stays at zero magnetic field. And I guess you all know that if you have a little magnet, and if you bring another magnet close to it, this magnet, your small little magnet, will actually get some finite energy. It will go to finite, somewhere at finite energy. So just the observation that our peak at zero energy stays at zero energy, although we're changing the magnetic field over a large range, immediately implies that the underlying particle is not magnetic. It doesn't change. It's not magnetic if it doesn't change in the presence of a magnetic field. Now next is to take one of these curves where we have a peak at zero bias and measure the electric field dependence. So if we change the electric field, will that move the peak to finite energy? So you see a similar graph here. Let me also guide your eye immediately to the zero bias peak. These traces are now taken at different electric fields, and the peak is stuck completely at zero energy. It doesn't move. So this measurement immediately implies that the underlying particle is also not electrically charged. If you change electric field, and if it's electrically charged, it will move to finite energy. It doesn't do it, so it's not electrically charged. So here, indeed, we have demonstrated 3 kinetics, 3 times nothing. It's no energy, it's at zero, no magnetic moment, no spin, and no electrical charge. The 3 kinetics are demonstrated. Now, we've done a lot more measurements, also some very detailed changing angles, and whatever thing you could possibly test on this Majorana fermion, we tested, and all the tests were pointing at a Majorana. So, have we indeed detected a Majorana fermion? That's the big question. Well, I can say that maybe with 6 sigmas, that the data reproduces. And we've at least 10 devices, and they all give you the zero bias peak. They all work in the same way. And also the data have been reproduced by other groups. If the other groups have made similar devices and they see the same peak at zero bias. So it reproduces. Now, it's not one experiment that makes us conclude that we have a Majorana fermion. It's really this whole set, this combined set of checking magnetic properties, electric properties, also angles, etc., etc. And it's this combined set that makes us to conclude that it's a Majorana. At least so far, it's inconsistent with anything else that people have put forward. So it is something that looks a lot like a Majorana, and I would say it walks and talks and looks like a Majorana. So is this enough to make the final conclusion? Or you could ask, what could you do more? Well, we could check its DNA. And the DNA of this Majorana fermion is actually very special. The DNA would show you non-abelian statistics. So what is non-abelian statistics? We all know about statistics. If you think about our quantum particles, then if we take 2 identical particles and we exchange them, then in the case these 2 particles are fermions, you get a minus sign for the combined state. If you do the same thing, but now for bosons, exchange them, you get a plus sign. And so far, all particles that we have can fit in in one or the other box. It's either a fermion or it's a boson. Now, our Majoranas are actually not in 3D. Actually, in dimensions, they are confined in a smaller dimension, 1 or 2D. And in 1 or 2D, you actually have the option to also have other types of statistics. And in this case, if we would be able to exchange two Majoranas around each other, we would not just get a simple minus or plus sign, we would get a different kind of phase factor. And actually, it even matters whether we go clockwise or anti-clockwise. So some brilliant people thought about this, and they start thinking about it in the context of information processing. So what if you put a whole row of Majoranas next to each other, and you start exchanging in the row different particles? And what you effectively do is you're adding complex phase factors to your system. And if you do it right, you can actually convert a simple string of bits into something that is more complex. You can process information. And in fact, you do this processing of information in this quantum way of using specifically the non-abelian statistics. So all you have to do is write your algorithm in this exchange gate, or what we call a braiding gate, and you have what's called a topological quantum computer. Now, these ideas, for a large part put forward by Alexei Kitaev and also Michael Friedman, actually came out of Microsoft. These people were working at a research station of Microsoft about a decade ago, and actually some of them are still there, and thought of using topology as a resource for encoding information, and hopefully in a much more robust way than ordinary quantum objects. And Microsoft has very generously also supported our research, and just the fact that they support fundamental science, I think is really worth a little acknowledgement here. It's courageous, I would say. So we have the signatures of the particle of the Majorana fermion. We know what we want to do next, demonstrate non-abelian statistics. So there's only one thing left: the man. So the man, Ettore Majorana, disappeared in 1938. Actually, some people, witnesses, they say they were Majorana's best friend in the 50s in Argentina. And there are other witnesses that say that they lived together with Majorana in some remote monastery somewhere in Italy. And so there are many different accounts of Majorana, that maybe he was living also after 1938. But no real evidence. Now, we found some real evidence for the man Majorana on the day that our paper got published. So what we saw when our paper got published, that we also had the cover of the science journal. Of course, to get the cover, what you do is you submit a whole bunch of different versions. And one of the versions was this real device, colorized with nice colors, the real device. But one of the students also made an artist impression. And an artist impression, even including little squares and rectangles and blocks that you can see here, maybe mimicking the granular structure of the metal. And it looks very stupid, right? At least I thought it was looking stupid. And I was really thinking, well, they must pick this one. But the result is, as you can see, that the art director of science picked the one on the left. Now, what the art director of science did not see is that we actually planted a little thing about the man. And if you look closely, and you know where to look, because if you look for a Majorana, it must be at the end of the wire. Always. So that's where you have to look. And if I can help you a little bit, that if you zoom in, actually you do see a little picture of the man Majorana. And we found actually, so we went on the internet to see who is this guy. And indeed, it resembles Majorana very closely. And with this tribute to the man Ettore Majorana, I'd like to thank you all very much for your attention. Thank you.